Okay, so this is the last PowerPoint for this section. All right, and so this kind of will tie everything together. So up this point, we said that acid and bases are where you give off a proton. If we think about what that means in the opposite sense, it kind of lets you know that when something becomes less positive, what does it also mean? It means it becomes more negative. And well, we spent a lot of time in 121 talking about that. And it turns out that all that talking about oxidation, reduction, and so forth, it basically can be all wrapped into acids and bases. And the fellow that kind of came up with all the tying us all together was actually pretty amazing, and he doesn't give hardly any credit at all to most the big world, Gilbert Lewis, in the 1910s, I know 100 years ago. He was coming up with ideas that were way ahead of their time that nobody had thought about and even think about. That turned out to be right, and it's amazing. And so Lewis, Gilbert Lewis, he looked at the acid base in a bigger sense than Arrhenius and Bronsted-Lowry, and he said, well, it can be looked at in a broader sense. And what we want to do is look at chemistry always in terms of electrons, because that's what makes it work. And so when you talk about a proton, losing a proton and so forth, that really doesn't make a lot of sense because that doesn't happen a lot. In fact, it probably doesn't happen. When we say H plus, when something loses a proton, it's just not that. Is what happened is actually the opposite. This is that it's giving away an electron and the proton's coming off. But so what Lewis came up with is a broad definition of acids and bases, and his idea is that basically he said that anything that can accept electrons is an acid, and anything that would donate electrons is a base. Well, just think about that. When we talked about 121, the things that took electrons were the things that got reduced. So things that get reduced are basically Lewis acids. And the things that give away electrons, donate in this class, are what we call Lewis bases. So what you have really is things that get oxidized and things that get reduced. And what that means is you have Lewis bases and you have Lewis acids. And that's it. You have the nonmetals, which tend to be Lewis acids. And you have the metals, which are Lewis bases. It kind of ties it all together. And we'll talk more. All right, so here's the example. Okay, Bronsted-Lowry acids give off H+. That means they lose positive charge. Well, when they do that, what do? They gain negative charge. Well, if you gain negative charge, what does that mean? Possibly you could be gaining electrons and become reduced. Right? And so Bronsted-Lowry bases accept H+. That means they get more positive. Thus I should be losing negative charge, which means maybe losing electrons. So if you put it in the big picture, which I'm going to fix this in a second, an acid is something that gains electrons, reduced, and a base is something that loses electrons, oxidized. All right, so let's look at some Lewis stuff here. Lewis, so you don't need to have Lewis acid base. You don't need to have in the water. The only thing you need to do is have an exchange of electrons. So we'll talk about three different cases. The first case is where you have a molecule like BF3 that has the ability to accept an extra pair of electrons because it's got a space for it. So boron has an empty valence. It has actually a place to put 2 electrons. So it can easily accept electrons. And so what happens is this guy here, nitrogen, has a lone pair of electrons. And what it can do is donate the electrons to the BF3. So the NH3 in a sense is now the base because it's donated, and the BF3 has become the acid. So the NH3 has been oxidized, Lewis base, and BF3 has been reduced, gained electrons. And they form a covalent bond. So if you take organic chemistry, you will see this type of reaction all the time, where you have this type of molecule is what you call electrophile, and because it can accept electrons. Electro means electrons, phile means love, and so this guy loves electrons, and so this guy can donate electrons to electrophile, and there'll be all kinds of chemical reactions that you'll see with that. Okay. So you have your base thing that's giving electrons, and you have, or oxidized, and then you have your acid that's being reduced. Okay, here's another example where of a Lewis acid base reaction is that, okay, you have carbon dioxide, and what it has is these double bonds, and these double bonds can spread out charge. But remember when we talk about resonance structure and so forth, is that these electrons that are in the double bond, they can move if it's allowed, if there's space on the oxygen, they can move to the oxygen because there's space for them, right? So this double bond can become a single bond, and the lone pairs can come out. So what happens here is this guy. So this is kind of a tack here. This guy is going to donate its lone pairs to the carbon. Again, kind of like an electrophilic attack. And what happens is that it's going to force one of these pair of electrons up on oxygen, and so you get this structure here. Okay, so what we just covered were these two, and I'll get to this third one in a minute. But so what happened was is if you have an incomplete valence shell like BF3, what can happen is that guy can accept a pair of electrons to fill a valence shell in a sense, and accept electrons. In the terms of carbon dioxide, you have the multiple bonds. The double bonds can be shifted to make room for electrons, and like CO2, what we just saw, and it can bond. Right. The third example is if you have a molecule, then it can expand its octet. So, usually when you talk about chemistry, it says an atom can only have 8 electrons in our shell. But in 121, we found out that's not true. What you can do is that there's if an atom has if it has d orbitals and so forth, d subshells, it can expand into it. So if an atom can expand its octet, it can take additional electrons. And let's take a look at that. So you have this. You have sulfur dioxide, and sulfur dioxide, it has all the 8 electrons around each atom. Blah blah blah. But what if oxygen comes here? And what oxygen does is it kind of comes in here and wants to grab a hold of all the electrons. And what it can do is attach to the sulfur and then just kind of explode it and open up the D subshell and expand the octet. And so now the sulfur, the oxygen is attached to the sulfur. And it's usually high electronegative atoms who will do that. They can kind of force open the sulfur, or in the atoms that can do that. So if you have atoms that can expand their octet, high electronegative atoms can kind of force their way in. This is kind of just tells you that Lewis acids are Bronson acids, bases, so forth. Okay, it kind of ties it together. All right. Just quickly, we could spend more time on this, but I'm not going to. This is more of a. I wish we could do more lab on this because there's more to it. But this doesn't have anything really to do with Lewis acids. It's sort of the last piece in the puzzle. Is that so you can how do you make acids and bases? Well, one way you can do is you can take a non-metal oxide. So like SO3, so forth, down here, and add water, and you can form sulfur dioxide and sulfuric acid. And when you do that, it lowers pH, which we'll talk about next. But these are acidic anhydrides. What that means is they're acids all ready to be. They're substances that are all ready to be acids as soon as you add water. And this reaction here kind of is kind of the thing that happens with it happens a lot. So this reaction here at the bottom reaction. So this reaction happens with the air. So there's carbon dioxide in air, and what it does is when it hits the water, like lakes, ponds, oceans, it'll form carbonic acid. And the carbonic acid will stick in the water, and what it does is it'll increase the acidity of the water, which can be a bad thing. Right? You can actually cause coral damage and all that kind of stuff. All right, and then you also can do the opposite. You can make a base if you take a metal oxide and add water. Okay, there you go there. And finally, this is the last one. So you take a non-metal oxide and you add it to water. You'll get, which one you get. It doesn't matter. It's the main thing is you end up with acid. Okay, so I'm going to fix this so you can get the right answer. So all right, so that's the end of this, and I'll get these online, and then you guys can work on them. Then I'll send out a worksheet too, so that you can try to just cram it in your brain and make sense of it. All right, thanks.